In this video, I want to have a look at binomial probability. So up until now, binomial is usually a word that we associate with polynomials and expanding them. But it's not surprising when you think about the fact that polynomials and their expansions and probability both have to do with combinations. So it's not surprising that binomials have to do with both of those things as well. So to be able to solve a problem, a probability problem using binomials, it has to satisfy certain conditions. So for us to be able to use binomial theorem in probability, our problem that we're looking at needs to involve multi-stage events. Every single stage has to be identical to the one before it, and each stage has to have exactly two possible outcomes. Now you might have things, the example that we're going to look at in a second is when we're rolling a die. Now obviously rolling a die has 6 possible different outcomes, but the way the question can be phrased can reduce it to 2 outcomes. So for example, the example we're about to look at is going to be the probability of rolling a 3. So now we have 2 options. We either get a 3 or we don't get a 3. So that way we can use binomial probability. So like I said, the example that I want to use to introduce binomial probability is going to have a look at rolling a die and whether or not we get a 3. So we're going to have a look at this experiment with having 3 stages. So we're going to roll the die 3 times. So I'm going to start off by drawing a tree diagram to represent it. So in our first branch, we're either going to get a 3 or not a 3. Then we're going to have our second stage where we can have a 3 or not a 3 as well. And then we'll have the third stage on there as well. All right, now along each of those branches, we can write in the probabilities. So the probability of rolling a 3 is 1/6, and the probability of not rolling a 3 is 5/6. So I'm going to fill that along all of the branches. Okay, so I've filled in my probabilities all the way along the branches, and I've also written all the possible outcomes at the end here. Now what I want to have a look at is the probability of different numbers of 3s. So probability of getting all 3s, or 2 3s, just 1 3, or no 3s at all. So I actually want to start looking at this second one here, the probability of getting 2 3s. So if we have a look at our outcomes here, we've got 2 3s in this one here, and this one here. So there's 3 different ways that can happen. And that makes sense when you think about combinations because we've got 3 positions here and we want 2 of them to be 3s. So we're going to write 3C2 because that's the possible number of ways we can arrange 2 3s and not a 3. So that'll give us 3 different ways. Now for each of those 3s, say we're going to figure out the probability of this one here, we'd multiply along the branches. So we'd have 1/6 times 1/6 times 5/6. If we went along for this one instead, we'd have 1/6 times 5/6 times 1/6. And this one we'd have 5/6, 1/6, 1/6. So in both of those, in all 3 of them, we've got 1/6 in there twice and we've got 5/6 in there once. Which makes sense again because the probability of a 3 is 1/6 and we wanted 2 of them, so we're going to square it. And the probability of not getting a 3 is 5/6, and we only wanted 1 of those. So now if we have a look at the probability of 1 3, so we could have that here in this one, or this one, or this one. So the probability is going to come out to be very similar. We're still going to have 3, but we're only choosing 1 of them to be a 3 this time. And we're still going to use the same numbers, but because we only want 1 3 this time, we're going to have 1/6 just once because there's only 1 3, but we want 2 of them to be not 3s, so we're going to have that squared. Now if we have a look next at the probability of all 3s, there's only one way that can happen. And that makes sense with our combinations as well because we've got 3 and we're going to choose 3 of them. And then we're going to have 1/6 cubed because we want 3s all 3 times. And the last one, the probability of no 3s is going to be this very bottom one here. Again, we're going to have 3 and we're going to choose none of them to be 3s. It's a 0, not a 6, which means we're going to end up with 5/6 cubed. So hopefully you can start seeing a pattern here as well. And that pattern is that if we wanted the probability of choosing n 3s, so n has to be a number between 0 and 3, then we're going to write 3cn, and then we're going to have 1/6 to the power of n times 5/6 to the power of 3 minus n. And we can generalize this even further to help us solve any probability problems that satisfy those 3 conditions that we had at the start of the video. And it can be for as many stages as we want. And rather than having to draw out our tree diagrams and figure out our probabilities, we can use this sort of notation instead. So our generalization looks like this. If P is the probability of success and Q is the probability of failure for an event, I should say event, not even, for an event, so that was the probability of getting a 3 and the probability of not getting a 3. And then we're looking at the probability of getting R successes in N trials. Then we can use the formula NCR, so that's the number of trials and the number of successes, P to the power of R, Q to the power of N minus R. So in our next video, we'll have a look at applying that to some examples, but that's an introduction to binomials and probability.